Okay, good afternoon, ladies and gentlemen. I'm sorry to disappoint you that the previous one was not the last presentation. So I'll try to keep it short. Okay, so I am Elina, and I'm from the Malaysian Palm Oil Board in Malaysia. And today I will be talking about a review of studies that have been done on real-time and in situ monitoring of crystallization of palm oil-based products using the Focused Beam Reflectance Measurement. Now, this is an overview of my presentation. I'll try to keep it short. We'll start with the introduction on palm oil, what is palm oil, and the technique that we use, which is the Focused Beam Reflectance Measurement, or FBRM in short. I'll talk about some materials and methods used in the experiments, and I'll go on to the results and discussion for each case, each oil, and then I'll conclude my presentation. Now, palm oil is the largest produced vegetable oil in the world, and in 2014, nearly 60 million tons of palm oil was produced worldwide. And as you can see, that palm oil, we get the oil from the palm fruit, which originates from the palm tree Elais guineensis. And palm oil is a vegetable oil which consists of nearly 94% of triacid glycerols, while the minor components such as the diacid glycerols, monoacid glycerols, and free fatty acids account for about 6%. Palm oil is usually used in a variety of industries such as the food, oleochemicals, and biofuels. And within the food industry, I think worldwide, palm oil is used for the production of cooking oils, salad oils. We also use palm oil for the production of margarines and shortenings, and also as a base stock for confectionery fats. Now, in order to make palm oil useful, in order to increase its usage in the food industry, it needs to be modified because it cannot be used as such. Hence, one of the most popular modification techniques for palm oil is the dry fractionation process, and this is a combination of controlled partial crystallization of the oil from the melt, followed by filtration of the crystallized slurry. And the first stage, which is the crystallization stage, is usually driven by the differences between the melting points of the constituent triacyl glycerols and the operating temperature. And in palm oil, there are nearly 19 major TAGs, and each one of these have different melting points. So as the crystallization process occurs, as we go down in temperature, then different TAGs start to crystallize. Now, from the point of quality of the products produced from dry fractionation, it is highly dependent on the operating conditions which we apply during the crystallization process. And also the crystal characteristics such as size and numbers and the shapes also have a profound influence on the subsequent filtration stage. And as you can see here, that palm oil can be fractionated in multiple stages to produce a variety of products, which in this case the palmolene is the liquid portion and the palm serine is the solid portion used for margarines and shortenings. Palmolene is used in cooking oils and salad oils, and when we fractionate it further, we get more subproducts which we use for more products in food industries, such as let's say high value low melting cooking oils, and also for confectionery fats. Now, why were these studies done? Well, most of the crystallization studies that have been conducted in the past in literature have been carried out on static systems, and some of them include using the differential scanning calorimetry, DSC, imaging analysis using polarized light microscopy, PLM, and also X-ray diffraction. Usually these studies, they do not accurately reflect the actual conditions in the industry, where they use a dynamic crystallizer, which we apply agitation to the slurry. This is partly due to the fewer limited numbers of tools or techniques which are capable of monitoring crystallization during real time. So Also, previous particle studies have focused on using image analysis, laser particle counters, and particle analyzers. However, some of these they require sampling the oil during study, and in some cases, we need to dilute the samples, and this causes changes in the material and study, and is not a representation, accurate representation of the actual conditions within the vessel. So. In the last decade or so, FBRM, or Focused Beam Reflectance Measurement, has been widely used as a non-destructive technique, which is capable of monitoring particles in real time and in situ, meaning that it does not interfere with the sample, and it does not cause any changes within the material. Now we'll look at what is FBRM. It's an in situ measuring device, and it tracks the particle size, population, and changes in events during crystallization in real time. It comprises of a probe in which we have a laser beam which passes through a sapphire window, and this laser beam actually rotates at a very high velocity, and as it goes into the suspension and steady, it will hit particles in its pathway, and the light is reflected back into the detector, and the time it takes for the light to reach the opposite side of the particle is then scattered back to the detector, and we can get a measurement of the size of the particle, which is termed chord length. And normally, FBRM measures particles in the range of nearly 1 microns to 1,000 microns. And this measurement usually depends on the crystal orientation, but in this case, for palm products, we usually assume a spherical shape. Now, for the crystallization experiments that we conducted, we used about 700 milliliters of the oil, and we subjected it to crystallization in a lab reactor, which is equipped with the FBRM, which is installed right into the solution. And we maintained the agitation speed at 50 RPM throughout the whole entire crystallization process. For different matrices, we crystallized isothermally at different time. For palm oil, it was 2 hours, and palmolene, which is the subproduct of palm oil, was crystallized for 6 hours, and the blended oil was crystallized for 5 hours. And also, we sampled the oil at different intervals and monitored the morphology under microscope. And at the end of the experiments, we took some samples and we filtered the crystallized samples, and we sent them for analysis. We analyzed them for the fatty acid composition and also the triacylglycerol composition. And this is just to see what type of triacylglycerols, or whether there were any differences in the types of triacylglycerols which would crystallize at different conditions of the crystallization. Now, let's just see what happens with palm oil crystallization. So we subjected palm oil to crystallize at 32 degrees Celsius, and as you can see, the FBRM detects the total particles within the crystallizer. You can see that a nucleation occurs about 150 minutes from the start of the isothermal crystallization, and it is indicated by a sudden surge in the total particle counts. And we also filtered the slurry at different time intervals, and we found that the filter cake, the yield of the solid portion, correlates well with the amount of total particles as reported by FBRM. Now, we also did a study on the melting of palm oil, whereby we crystallized palm oil at 24 degrees Celsius, and we subjected the oil to heating at 2 degrees intervals until the oil fully melted, which was at 46 degrees Celsius. And we can see that we can look at the fine and coarse particles. In this case, we can see that the melting mechanism of palm oil consists of melting of the fines, which followed by agglomeration of the particles, which is signified by a sudden drop in the coarse particles, when there's a sudden drop in coarse particles, that means that, and an increase in fine particles, that means that this is the agglomeration of the crystal structure within the vessel. And now we'll move on to palm olein crystallization. We managed to do a study on the subproduct of palm oil. We crystallized palm olein isothermally at 9, 13, and 15 degrees Celsius. And as you can see here, this is the total counts versus the isothermal hold time. And we can see the different mechanisms that govern the crystallization events at these different temperatures. For instance, at 9 degrees Celsius, we can see that there's a primary nucleation. Actually, primary nucleation occurs at all temperatures, but we can see that there's an agglomeration event which occurs towards the middle of the experiment, and this is signified by a drop in the total particle counts. And for the crystallization at 13, we can see that it is it occurs in a two-step manner, where we have a primary and secondary, which is signified by a sudden change in the sudden increase in the particle counts. And for the crystallization at 15 degrees Celsius, there is only a single-stage crystallization, which is signified by the primary nucleation with a sudden increase in the particles. And this is we come to this conclusion based on the fine and coarse particles, which I have not reported here. Now we looked at the crystal size distribution of palm olein through the FBRM, and also we looked at the crystals under the microscope, and we found that the FBRM data correlates well with the images from the polarized light microscope. We can see that at 15, there's a very small number of crystals, and this is indicated by the area under the curve, and this was also previously indicated in the total particle profiles. The size of the particles more than trebled when we increased the temperature from 9 to 15, as you can see here. The large particles at 15 become smaller as the temperature is reduced, and in the case of 9 degrees Celsius, you can see that there's the crystals start to agglomerate, they start to stick together and to form a crystal network. This is due to the large amount of crystals produced at the lower temperature due to the high driving force applied at these conditions. Now, we looked at the composition of the fractions at these different temperatures, and we can see that as the temperature is reduced, is decreased, we can see that there's an increase in the amount of monounsaturated fatty acids and MUFA, and corresponding decrease in the amount of saturated fatty acids, and the PUFA did not increase much and sort of remains stable. But this result indicates that as the temperature goes down, we have the more unsaturated components starting to crystallize out from the slurry, and this also is indicated in the iodine value, which is a measure of the unsaturation of the oil, and this goes up. This goes up as the temperature goes down. Now we looked at the major triacylglycerol groups in palm olein, and this also indicates that as the temperature goes down, the amount of the unsaturated components go up. The diunsaturated and triunsaturated TAG components, they increase with decreasing temperature, while the monounsaturated components, which comprise of two saturated fatty acids, increase with increasing temperature. Now, we also did a study on the effect of blending palm olein with a legume seed oil, which was wing bean seed oil, to see whether we can see whether the legume seed oil behaved as an anti-crystallizer or as a crystal promoter. So what we did was we blended palm olein with two ratios of wing bean seed oil, which is a tropical oil in Malaysia. It's a four-angled bean, which is usually eaten raw. And from the seeds, we extracted the oil, and we mixed it with palm olein in 2.5% and 5% ratios. And as you can see, that we subjected this to crystallization at 13 degrees Celsius, and we found that with the addition of the wing bean seed oil, when the wing bean seed oil increases in ratio, the initiation of nucleation is shortened. That means that it is a crystal promoter in terms of nucleation. Also, we can see that as the amount of wing bean seed oil increases, the number of particles also decreases. So this means that besides acting as a crystal nucleation enhancer, it also does not allow more crystals to form. So it's like a dual role. And we looked at the crystals under the microscope, and also based on the crystal size distribution from the FBRM, we found that it agrees with the previous results. This is the control palm olein, and when we added the wing bean seed oil in different amounts, we saw that the number of crystals decreased, and also the size of the crystals also decreased, meaning that they not only serve as a crystal nucleator, but also a crystal growth retarder. And this means that we cannot use this as a crystal promoter in palm olein crystallization. We also filtered the crystallization slowly, and we subjected it to fatty acid composition analysis, and we can see that in palm olein we only have about 6 major fatty acids, and with wing bean seed oil we have additional fatty acids with C20 chains and above. And we can see that as we add the wing bean seed oil, we have an increase in the behenic acid, which is a very long chain saturated fatty acid. And palm olein has been shown by previous literature to be an oil which is difficult to crystallize. So with the addition of wing bean seed oil, we can see that the behenic acid played a role in promoting the nucleation with these small amounts. However, we saw that during the crystallization, it also did not allow further crystallization to occur. So it has a dual role in palm olein crystallization. So I've come to my last slide. I just wanted to conclude my presentation that we found that FBRM is a useful tool for monitoring in situ and real-time crystallization of palm oil-based products and oils and fat systems in general. And we've been able to obtain valuable information such as the crystal population, size distribution, and also the different mechanisms that occur throughout the crystallization process. The advantage of using this technique is that the data is obtained in situ in real time, so it's closely representative of the actual process conditions. And if we complement the FBRM data with microscopical images, or maybe more sophisticated particle video microscopy, which is a very expensive microscope which you put the vessel, I believe we can get more information on the actual conditions within the vessel. And lastly, the use of FBRM enables proper control of the operating conditions during a crystallization process, and this also ensures that we get to produce the optimal crystal characteristics for usage in a variety of food industries. And before I end the presentation, I would like to invite you to the International Palm Oil Congress, which our organization is organizing, which will be held in Kuala Lumpur, Malaysia, from the 6th to 8th of October 2015. And hope to see you there if you're interested. And thank you for your kind attention.
Thanks very much for interesting presentation. Questions?
Everyone wants to go home.
Everybody's tired?
Yeah.
So, okay, then I thank you again for your presentation, and I hand over the certificate. It's my pleasure.